Mark Hurd will kick off the formal program this morning, and I believe the fact that Mark is here as Oracle's co-president and a member of the Oracle board underscores what I was saying earlier about the direct relevance of SPARC's remarkable history to the future roadmap of Oracle, and you saw a little bit of that this morning. Mark, of course, has been a leading figure in information technology at the CEO level for more than 2 decades. He's an important part of Oracle's visionary leadership for the future, and he's going to talk to us a bit about that future now. Ladies and gentlemen, Mark Hurd.
Great. Hey, listen, I've got just a couple minutes, and I thought what I would do is first tell you a little bit about Oracle. You know, what we're doing, what we're working on, and then try to tell you how SPARC fits into it. First, company. I don't know how closely you guys follow us. Company now, 120,000 people at Oracle. So big company. Our revenue, we're actually, oh, that's so nice of you, John. You could, yeah, thank you. We're actually in our quiet period right now, which means I can't talk about much of anything other than my name and address. But our revenue is probably estimated by others to be more than $40 billion in this current fiscal year. We spend about $5 billion a year now in R&D. We spent about 4.3 2 years ago, about 4.5 last year, probably headed to spending about 5 this year. So think of 14 billion of R&D over the last 3 years. And then most of you probably know we buy companies. We've got about $32 billion worth of cash. We make, it's a lot of money, a lot of money. And because we have an owner, he counts it, you know, frequently. But we have, we're about $32 billion worth of cash, and in the bank it makes less than 1%. And we make better than 1% running the company, so we invest it in the business. And so think of that as a supplement to R&D. Last year we spent $6 billion on M&A to grow the company. So a lot of people, big R&D bill. We're investing back in the company, and we've got 4 strategies in the company. Basically to be best of breed at everything we do. And I'm going to tell you more about that in a second because it reflects on SPARC. Everything we do we want to be best at, whether it's database, operating system, apps, etc. Everything we want to be best of breed. Second, we vertically integrate these technologies into these things you're going to hear terms, I hope you hear. If you don't, the marketing department has more work to do. Things like Exadata, Exalogic, Exalytics. These are where we actually take the silicon, the OS, the database, some cases all the way to the middleware and even the apps, and vertically integrate them together. We can run these systems tens and tens and tens of times faster and actually lower the TCO while we do it. Third, for us, we're doing a lot of work in the cloud with applications and what you'd call SaaS and infrastructure as a service and platform as a service. And fourthly, we're building out our industries, financial services, healthcare, et cetera, et cetera. These are 4 strategies that we think can put us in a position that makes us, frankly, the leading IT company in the world, measured by both revenue and margin and customer acceptance and customer satisfaction, et cetera. And we're working really hard to make that happen. Now, in the context of SPARC, I don't know, you want to show a quick chart? You know, sort of at the time, we may go back to that chart, but at the time that if you look over this period, there's this company, I can't read their name, that's in the blue, and historically, they've had, at least over the past, and I think if you drew this chart back in time, you would find at one point, many of you remember SPARC having the technology and microprocessor leadership in the world. Best performing chip in the world. And that position over time waned. You can see what's happened sort of when the introduction of what was called the P5, Power 5, back in, John, what would you say, 2005, 6 time frame, something like that. They sort of took the leadership from both Sun and HP and frankly went on a run. They introduced the P5, they introduced the P6, they introduced the P7. They had sort of a new processor, seemed like coming out every 18 months, and they took a lot of share. I want to tell you here and now, we've made a lot of progress. The T4, which is on this chart, is the leading Unix systems product in the world. Right now, the hottest Unix computer in growth rate is the T4. By the time we release the next generation product, which I won't release to everybody, we're in quiet period, so I can't talk much, all this stuff, we will take the microprocessor lead from IBM. You have my commitment on that, and you have, more importantly, Mr. Ellison's. He has become a chip zealot. And I think John will tell you when he talks more and more about SPARC, and frankly, this whole point about best of breed. We have to be the best, not just at these combined systems, but at every piece of the architecture. So you have our commitment on that, to that leadership at every point of the stack. And to be blunt with you, it's more than just silicon, because we're doing more things than just the silicon. We're now putting software onto the silicon. It's what's changing our position in analytics, putting more software directly on the microprocessor. Same thing with compression. We can now compress the Oracle database 10 times. You had a terabyte, now you got 100 gig. Got 10 terabytes, now you got a terabyte. You get the. We do that through columnar compression and software that we can now further integrate in with a silicon design. This not only gives us best-of-breed leadership in silicon, but best-of-breed leadership in overall systems performance in TCO. And at Oracle, we're committed to this. So probably a different Oracle than you knew. Probably now a different Sun within the context of Oracle, at different advantages that the company and the technology never had before. So I hope you feel, for all of you that were part of this from the get-go, technology's in good hands. I don't want to say deep pockets, because we might have short arms sometimes, but deep pockets. The ability for us to invest, to sustain the technology, to integrate the technology with software, to turn those into systems that frankly revolutionize the world. Now, I could tell you a lot more about other things in the industry, but for the sake of the day, the message I wanted to give you was really around Oracle, Oracle strategy, Oracle's commitment, and thank all of you that were part of the beginnings of this technology, and let you know we're committed as we go forward in the future. Okay, thank you.
Congratulations, everybody at Oracle and all of the former Sun folks and the current folks working on the SPARC architecture. 25 years. That's an amazing, amazing run. That's a lot of legacy. Makes me feel old as a formerly important and famous person. It's great to see the SPARC architecture, the technology, and the value that you bring to the market live on. Keep up the great work. It's good stuff. So everybody looked at the launch of SPARC and said, what are you trying to do? How can you compete against Motorola and IBM and Intel and all the others in the microprocessor space? And the answer was simple. Nobody was delivering the kind of performance, the floating point, and the technical computing power that we needed for our engineering workstation marketplace. Nobody was building in to drive the graphics and all the other technologies that we needed for the engineering workstation space. So we had to go do it ourselves. We asked Motorola, we asked other companies, and they were too focused on the PC market, which turned out to be maybe a better place longer term for them to focus, but we needed more horsepower. So we went off and invented our own architecture and went with RISC, and RISC was reduced instruction set computing. Simple computing, simple architectures that were more manufacturable, more scalable, and significantly more powerful. We pretty much knew we had a hit when we finally got the chip back and we plugged it in and it started wiggling and we started doing the benchmarks. At the time, the engineering unit of measure was the VAX at 1 MIP, and all of a sudden we were launching a little small desk-side computer server at 7 MIPS at the low end and 10 MIPS at the high end. This was an order of magnitude faster than the VAX and way less cost. It was pretty clear from a price performance standpoint, we had a huge winner. You know, SPARC just really changed the marketplace in several ways. One was, it was the first microprocessor that had all of its computers shipping with TCP/IP. Seems like obvious now, duh, but back in the mid-'80s, TCP/IP was competing with IPX, LAN Manager, Token Ring, and all of the other architectures out there for networking. Then we threw on top of it Open Unix, and that wasn't a natural and obvious win for a lot of other companies that were going with Windows or with Apple's operating system and a lot of the mini computer and mainframe operating systems. And then you threw on it the RISC architecture with the performance that it offered, and finally our ability to deliver it at low cost. And the SPARC really took off when we launched the SPARC Station 1 at $49.95 for a desktop computer. Boom, we were blowing the market away, and you add all of those pieces together, and we had a magical cocktail that exploded into the technical and other marketplaces. So SPARC had all kinds of features, capabilities, functions that we needed the software to take advantage of. We needed the software to inform the user of all of the capabilities that were in the hardware. And the only way that was going to happen is if we had our own operating system. And we had one that was open, one that we could modify, one that we had rights equivalent to ownership to go operate. And we had that with Solaris. We had that with the Unix operating system. And we could basically bring out a system. Having software separated from hardware, sort of like Intel and Microsoft, has huge issues, and performance has never been the #1 key, nor necessarily the most aggressive growth path. So having those two together and the ability to launch a system, we always called ourselves Sun Microsystems, not Sun Microsoft or Sun Microchips. We were Sun Microsystems, and we always looked at launching that system. And I think that's the big advantage Oracle has now, is they can go all the way through to the applications, the middleware, the database, and the entire stack, and launch a system. We used to call it the network as a computer. Now it's called the cloud. Well, you know, everybody asks me, what are you going to do? What are you doing? What have you been doing since Oracle? Well, I lasted 2 days after a change of control, and some people are arguing that was a paperwork snafu, but no, we left on good terms, and now I'm doing videos for Oracle. But I'm also chairman of Weigh-In, and I want everybody to check it out, WAYIN. It's a new social media environment that actually has value to corporations. I'm still driving Curriki.org, K-12 open source educational materials. We have over 7.5 million unique visitors now to Curriki. And I'm doing lots of consulting and advising on the side to anybody and everybody who asks me for help. I don't charge much, which means I have infinite demand. And I'm coaching my 4 boys in hockey and having a ball raising 4 future entrepreneurs. So life is good, and I miss all of the Sun and SPARC folks. Keep up the great work. We're all counting on you to continue to deliver the next generation of computing.
Of course, Vinod was so instrumental in building the whole Sun platform, and now has gone on with Khosla Ventures to invest in the technologies and the companies and the causes that he believes in around the world. So Vinod, I'm going to ask you to come up, and we'll hear from you about those days and those memories, and to thank you for everything that you've done to help make this day possible. Vinod Khosla.
Thanks very much.
Thanks, Vinod.
It's great to see so much interest. It's exciting to see so much interest. I was sitting there talking to Andy and saying, if we knew everything we know today back when we started the SPARC project or the Sun project, we would never have started it. There is real truth to ignorance is bliss. I mean, there are so many reasons things could have been different, should have been different, should have failed. And so it's great to be here. Any good project has a very, very large dose of luck. I think in '86 was the first time I was asked, how come you got so successful? And I said, I'm really good with Lady Luck. But what I thought I'd do today is give you a little bit of story of how all this originated, where SPARC originated, what the thinking was, And little anecdotes that you might not otherwise hear. I've generally not seen them reported. Sun was, of course, started an open systems company. There was a problem, though. It was also the most criticized feature of Sun's business plan. Nobody thought you could build a proprietary system out of open components, and why wouldn't competition drive you down? We looked at it a little bit differently. We were trying to steal all the engineers 3Com had in networking, and I forget the name of the company, doing disk controllers and all the components that we had to assemble to then compete with HP. HP was the smallest major vendor in the computing business. I think they had about 300 engineers in Fort Collins, Colorado. And we had to match that in terms of our engineering resource, and with a few $1 million, we couldn't do that. So open source was really much more necessity than a vision when we started. It was leveraging everybody else's work and leveraging their efforts. But because open source was not proprietary, one had to have differentiation, which is when I first fell in love with the idea of doing RISC processors. Turns out we needed to have something. Turns out that IBM wasn't going to do it because it didn't fit in their product line. In fact, IBM did have one mainframe machine called the 9370 that had a RISC architecture. But they had plenty of no-op instructions inserted in it so it fit in their price performance product line. And I remember thinking about that and getting very frustrated. DEC, of course, was in a place where Ken Olsen didn't believe anybody needed personal computing. I think he was on the record doing that and saying that. Hence, the idea of SPARC was born. It'd be the differentiation we needed. It'd be the oomph we needed to beat everybody else, and nobody else was doing processors. But none of these things are actually easy. So there's 20 things that could have happened that could have caused us not to be here celebrating the 25th anniversary. First, Sun had never done a chip. So there was lots of reasons not to do SPARC inside Sun. Sun had never done a chip, as Andy reminds me. Sun had many crises going on. We had this problem with monitors blowing up. Our average lifetime for a computer monitor shipped with the Sun was 30 or 60 days. Believe it or not, and I don't believe this story has ever been written, we almost went bankrupt back then. I think the earliest I ever left work was 3 a.m., and the latest I got in back to work was 8 a.m. during those days. So there was lots of reasons we shouldn't have done SPARC. And because of everything going on, we'd taken on this whole job of an operating system and things that no other computer company was doing, that there wasn't a lot of interest internally in doing SPARC. Dave Patterson's here. Bill knew Dave, but we got to Dave as an outside consultant. Maybe Dave will reaffirm that. I was trying to recollect exactly the memory this morning. I sent Andy a quick note at 6 a.m. saying, do you remember it this way? It's hard to remember everything with high fidelity. But our customer support group, a guy called Steve Saperstein, introduced me to Dave first. They were doing customer support for Berkeley. And that's how the initial architecture effort got started. But there were other reasons. First, as soon as we got interested in this, Motorola came up with their own RISC version of the Motorola 68000 and tried to convince everybody at Sun that SPARC was not needed and Sun shouldn't be doing it. Not only that, there was a guy called, I believe his name was Skip Stritter, who I tried to recruit for 6 months to do the SPARC project inside Sun. And he decided, of all things, to do it outside. So he started MIPS Computer 6 months after we'd been trying to recruit him. And so there were many, many setbacks along the path of getting Sun started. But the project was started, and you'll hear the details from Bernie and Anant and Dave and Bill Joy and Andy, I think, will come talk about the history of SPARC. But there are so many little stories why this wouldn't have happened. But let me just say, my favorite story of all is, by then, the big problem was Sun was actually growing pretty rapidly and getting to be then what we considered a big company. And there was starting to be politics. So at one point, Andy and I decided to do something that later was called the SPARC station outside of Sun. One more additional anecdote. We decided to spin it out of Sun, formed a company called Unisun, and we were going to venture fund it. I'd by then moved to Kleiner Perkins, so Kleiner was going to fund it. And we set up in a separate building, hired a team that lasted for maybe 2 months before Sun said, oh no, let's just acquire this back. The goal wasn't really to start a company, it was to force Sun to do this project, which was the SPARC station, which immediately became a billion-dollar product line, which even for a big company, Sun was relatively small compared to a billion-dollar product line. So those were some of the interesting stories I wanted to share with you. But I want to share 2 other things. You know, the story of SPARC is interesting. Looking at the odds of it being successful is also very, very interesting to me. But the one message I want to leave all of you with is no matter how improbable something looks, it's worth attempting. If we hadn't been naive or more foolish and risk-taking than we should have been, in retrospect, I'd clearly say there's lots of risks we took that we shouldn't prudently have taken. I would urge you all to use this as a model to say, go try it, go do it. George Bernard Shaw has a quote that I use repeatedly, and SPARC is an example of that. He says, all human progress depends on the unreasonable man. He should have said man or woman, but I'll quote him with high fidelity. So I urge you all to do this. One of my laments as I look back over the last 10 years or so is there's very little innovation going on in computer architectures. With the possible exception of what's going on inside Google, there is almost nothing new. It's the same architectures, no major architectural change. It can't be that 25 years, there's no need for an architectural change. There's plenty of relabeling to cloud, but it's the same microprocessors, the same architecture, when so many new things have shown up. SSDs didn't exist. Network speeds and processors had different I/O ratios. So the optimization's different now. I could go on and on. But I do urge people to go innovate again and take larger, bolder risks. I got frustrated with this about 3 years ago and started looking at it. Because of that, we've invested in a computer architecture company called Nutanix. We've invested in a new router company after I'd done personally worked with Pradeep on Juniper. Software-defined networking is changing a lot of things and a lot of assumptions. Almost certainly, the right architecture for storage is not EMC or NetApps. So many things have changed, a completely different optimization is now required. So I urge you all to look at that, to think about it, and actually go do it. Be bold, be foolish, go attempt it. Lastly, I would say it was just such a great pleasure to work with the people at Sun. Even to this day, I've met few people like Bill and Andy when it comes to understanding technology well and thinking clearly about it. It's probably one of the best things that ever happened to me is to meet people like Bill and Andy and others at Sun, and there was quite a few. In fact, when I looked at the history, and I haven't compiled it, the Computer History Museum should, but the first 15 or 20 people must have spun off 20 companies, 10 of which were probably, I'm just guessing, but somebody please verify it, but don't quote me, that were worth $1 billion or more. That was because of the quality of the people in the early team at Sun. And that probably has been the absolute best thing that ever happened to me. Thank you all very much, and it's a great pleasure to be here.
History at the Computer History Museum is a wonderful blend of curators and volunteers and the people who made history. And one of the hardest working people who fits into two of those three categories for sure, and who helps the museum so much, is Dave House, who's the vice chairman of our board and is the chairman of the Semiconductor SIG. As I mentioned earlier, the SIG does a tremendous amount of work in the area of semiconductor history. And every once in a while, Dave will be part of an absolutely sterling panel which presents history both in the words of the people who made it and in the perspective that they've had after many years of experiencing it. Dave, as you probably know, had a long and distinguished career at Intel, was the chairman and CEO of Bay Networks, is now the chairman of Brocade. And he and the panel are going to come up now. He is going to moderate for about the next 45 or 50 minutes. And I know we're in for a real treat with him running the show. Dave and the panel, welcome.
It's a great honor to be here. What a group of rock star technologists and business leaders we have with us today, huh? The biographies of the people on this stage would take the rest of our allotted time to cover, and I think most of you know about them. So let me just comment about their involvement with SPARC and Sun Microsystems. Dave Patterson, professor of computer science at UC Berkeley, during this time has served as a consultant for Sun from the very beginning until its acquisition by Oracle. Bill, of course, did his initial work on BSD Unix also at Berkeley, but was co-founder of Sun Microsystems and obviously a key member of the architecture and software teams there. Andy Bechtolsheim, really the genesis of Sun, with the work done at Stanford with a workstation design there that became the beginning of Sun before SPARC, and was co-founder and chief system architect at Sun, led the development of the SPARC Station series of workstations. Bernie LaCrue joined Sun very early in 1983, assembled much of this crew outside of the founders. He was VP of Engineering, Executive VP of Engineering, Manufacturing, Marketing, and a board member at the company and a key executive making this whole thing happen. Anant Agarwal came out of the semiconductor business to join Sun at the beginning of the SPARC processor program and wound up managing many of the various SPARC implementations at Sun throughout his career from 1984 to 2002. And Rick Harrington is Vice President of Hardware Development Systems at Oracle, and at Oracle, well, he joined Sun in '96 as co-architect of the Sun's Project Millennium processor, and Oracle's responsible for the SPARC architecture and its performance. So I think I touched all of them. As I said, they didn't need much introduction. Let me start out with Dave Patterson, because SPARC RISC processor came out of work at Berkeley. What were you doing before you first heard of Sun?
I was, well, I think I joined, got my PhD in '76 and joined Berkeley in '77, and I think that's about when Bill got there. And I was just thinking that we did a class when Eric Schmidt mentioned the Burroughs architecture. There was this idea, this high-level language-oriented architecture that closed the semantic gap. So I taught a course in it, and there were like 10 graduate students in the course, and the course had Randy Katz, who worked with me in RAID, Eric Schmidt, and Bill Joy. And I remember I still remember right from the beginning, it wasn't clear who was going to get more words in, me or Bill Joy. And
it's still a debate.
Yeah. But, you know, we, at IBM, there was John Koch, who led this research effort. They were doing an ECL mini computer around PL1. they really didn't understand VLSI at all. I think he visited Stanford and Berkeley to try and get us to work on it. I didn't do anything until I took a sabbatical at DEC, where I worked on the VAX. Hennessy and I had both done microcode tools for our dissertation, and I was kind of aghast at how many bugs there was in the VAX. And so when I came back in January, we started a sequence of courses, which I saw some people who took those courses that explored those RISC ideas. So Bill was there as a graduate student, and of course at Berkeley, what were we going to do? We were going to do C and Unix because of the BSD stuff. Bill had opinions on everything, so he was, kept up with what was going on, and we built a bunch of chips. They worked really well, and it was still amazing to me at that time. Berkeley graduate students could build a chip that was actually faster than what Intel could build, and that was, we demonstrated that in '82 or '83. But Bill went off to do Sun, and I hadn't seen him for years. Then he came and visited me. I was consulting for Xerox PARC on Smalltalk and stuff like that. And boy, it just seemed like no idea at PARC was ever going to make it commercially. And Bill, Bill dropped by and said, "Hey, I'm starting this, this company, and we want to do RISC." And I just thought it was crazy that a company the size of Sun was going to do their own architecture. But I think that's my introduction to the story.
So what role did you play in the SPARC architecture over the years? We were there longer than anybody, never an employee, but always a consultant.
Yeah, they didn't realize that tenure applied to consulting as well as to... and apparently if Oxford buys Berkeley, I'll lose tenure or something. So I lost my tenured consulting job. Let's see, what was the question?
So what was your role in the architecture during this time?
I was the first guy they hired to do SPARC, and I helped recruit Bob Gardner, who was at Xerox PARC, who I'd met, and to help get this started. And I was there to try and give sage advice on what to do architecturally, who to help recruit, and things like that.
So Bill, you were part of the founding team, and so started out with a 68,000 based product. Why not stay with that line of processors? What gave the spark for SPARC?
Well, I was always concerned about doing numeric and symbolic computing as well as the generic C code. I'd worked on the Cray. I'd written code for the Cray and the Cray, the TASC, the ILIAC, that class of supercomputers in the 70s. And so to my mind, a proper system ought to launch a floating point or operation, ideally a floating point add and a floating point multiply every clock on the numeric side, and should also have good support for Lisp and Smalltalk, so it ought to have support for tagged operations on the other side. And so I saw an opportunity. This clearly wasn't where microprocessors were headed. Intel had gone off into an 80-bit floating point, which wasn't going to be of the performance that the scientific computing really needed, I thought, and I didn't see the support for symbolic computing in the instruction sets. So when we had this opportunity to do SPARC, I was really focused on supporting those kinds of things, and I pushed many times in the initial architecture and also in the revision for 64-bit to really push in these directions. So there are probably many stories about, say, for example, why SPARC has register windows, but I would have laid down the tracks to prevent it from being deleted, because while you could register color in the compiler for C, you could never register color for the more dynamic languages. And I firmly believe that more dynamic languages, which became things like Java in the end, were the future of reliable software. And I wanted to have a hardware platform that added the few transistors that you really needed. It isn't very much. The tagging instruction was like 2 AND gates or something. I mean, there's very small changes you could make to add these facilities to support what I saw as the future directions for the software. And it goes all the way through to us pushing very, very early on for threaded. I was a very strong proponent of multi-core and multi-threading in the microprocessors. So I saw it as our way to get lined up for the future of software and systems that I saw coming.
So you started out in software with BSD, Unix, and then somehow sounded like you became a chip designer. How did that happen?
Well, I helped design the SPARC pipelines. I have notebooks in my file cabinet, historical file cabinets full of pipeline designs. UltraSPARC 1 was a pipeline I designed and was later implemented by others. But you know, it's really, I hadn't wanted to do it when I was at Berkeley because at the time the CAD tools were so primitive. It was basically drawing colored squares on a graphics display. That didn't seem to be a good use of my time. But I got in a very position where I could work with really great chip designers, and we did some really interesting pipelines for SPARC.
So what did you see as the vision for SPARC at the time SPARC was created?
To get us into a situation where we could, like the supercomputers I'd worked on, you know, launch and retire multiple instructions per clock, and with the clock rate at least as fast as the SRAM could be, you know, as fast as the cache could be, and even looking at interleaved caches to run the heartbeat of the processor at twice the cache speed if we could figure out how to do that. So we had the opportunity of extracting a lot more performance out of a given node of technology than the 68000s or x86s.
So Bernie, what were you doing before you first heard of Sun?
Well, I had spent 14 years in another computer company called Digital Equipment Corporation. And actually, I was the product manager for the VAX program, which maybe we can have a panel for sometimes later this year or next year. That's 35 years. The first VAX machine shipped in 1987.
Harder to find a corporate sponsor for the VAX, I think.
Well, yeah, that's probably true.
So that's a big job at a big company. Why did you leave Digital to join Sun?
Well, actually, it's fairly simple. I was pretty frustrated. Vinod alluded to some of those issues before. DEC was extremely successful, but was wedded to the time-sharing model. So there is no way that we could change the business model of that company and go and build either a workstation for engineers, which was the root of what DEC was all about, or personal computers. So I was frustrated because actually we had a workstation running in a lab called SUVAX, single user VAX, and we just couldn't bring it to market because the CEO was stuck in his way of time-sharing model, great business, but couldn't see beyond that. So that's the reason.
So one of the things you did is you hired an amazing team of people, you know, coming in shortly after the founders. And how did you get these people? How did you manage to assemble such a team? I mean, Sun it's had great engineers throughout its history, but the initial team at that time was just an amazing team. How did you do that?
Well, first of all, I mean, the hiring effort was a group team effort. There was nobody that would not go and try to go and get the best talent we could possibly get, whether it be Bill, Andy, Vinod, Scott. We all got together and said, this is the person we want. Whether a guy or a woman or whatever, that's the best for the job, and go after it relentlessly and go and hire those people. We had a say at Sun that said, there is no replacement for brain power. Brain power is what it's all about. So you go and identify the people and go and recruit them. Is it a management challenge? Yeah, it can be. But you know what? Brain power beats every other alternative. So just as Vinod said, you know, don't take a risk, but also go for the talent. It doesn't matter if the people are older, have a lot of experience, or if they are very smart. Go for the talent.
So you were VP of Engineering. You must have had some interesting challenges in those early days of SPARC. Can you tell us about some of that?
Yeah. Certainly at the time where SPARC was started, we were in an interesting situation. The monitors had a lifetime. I think Vinod said 36 hours. My recollection is more like 2 hours. Actually, at one point, we were shipping 2 monitors for every machine we built because they just were not working very well. So there was a little bit of an engineering problem there. There's also a bit of a cash problem, as Vinod alluded to. I mean, you know, if you ship 2 CRTs per machine, consumes a lot of energy and resources. So we had our share of problems on the engineering side. The SPARC was really a challenge in many, many ways. I mean, obviously, Sun had never built a chip, but also we didn't have any of the CAD tools that are common today to build those chips. I mean, I remember doing some of those timing analysis by hand. Where was the CAD system? We ended up using the DAISY workstation at one point. But I mean, it was a heck of a challenge to go and try to design something from scratch.
So the origin of SPARC really, the concept came out of RISC-1, I guess, at Berkeley, but then you did your own architecture or your own version of that. How did it get called SPARC? Where did the name come from?
Oh, I don't know. I think I will let Anant cover that one because he is more current on the name than I am. Go ahead.
So it's an interesting story. At Sun, when we started any program, it was a fairly formal process to name it. So we would call the entire team in a room, but before that, we had a few names and they would vote on it. Well, in this case, when we started SPARC, it was a fairly small team. So we had an engineer called Will Brown, and Robert might remember that. We told him we need a four-letter acronym, so he wrote a program. And spitted out these pages and pages of names, and then we got together, and we liked the name SPARC, but what in the hell does it mean, you know? That's when we, I think, got hold of Steve Diamond, and we tried to figure out what should we say SPARC means. So we came up with this thing called Scalable Processor Architecture. So, very scientific way.
So Anant, before Sun, you were designing chips. You came out of the semiconductor business. Sun's a systems company, never designed a chip before. How did you come about being employed at Sun?
Yeah, it's a kind of interesting story. I came in and got brainwashed by Bill and Patterson, Bernie. I don't know, Andy, if I talked to you. So I was driving back that day. I recall this very vividly. And the same thought you heard before from Vinod or Patterson was, and this is really true, this is what went through my mind. These guys are Looney Tunes. Okay? They have never done a chip before, and now they're trying to do one of the most complex pieces of silicon, which is a microprocessor, right? Then as driving more, you know, I thought more about what Bill and Patterson told me about their vision. And I said, you know, this is a crazy group, but if there's any crazy group that can pull this off, it's these guys. And because they know what they're doing, at the same time, they don't know what they don't know, which is designing chips. So I kind of leaned more towards Sun. I had offer from Amdahl, Hewlett-Packard, another startup doing OCR. And then I was still struggling, and strange thing happened to me on Sunday. I was, at that time, my wife, she was my girlfriend at that time. So I was invited to her home for breakfast on a Sunday morning. No, Saturday morning. And I recall in those days, Bernie, on Saturday was a recruiting day.
Every day was recruiting day.
So somebody called Vinod called my condo that I was sharing with my two housemates. And he convinced them to give him my girlfriend's parents' home number. I don't know how he pulled it off, but he got it. So I'm sitting at the table about to start the breakfast, the phone rings, and my girlfriend at the time, she says, "It's for you." I said, "What do you mean it's for me?" Anyways, in those days, there weren't a lot of wireless phones, so the phones used to have a long cord. So we were sitting in the breakfast nook. She kicked me out to the garage. And she says, "You go do your business. We're going to have breakfast." So I was in the garage for an hour talking to Vinod. And after that hour of conversation, I said, "Vinod, I'll start on Monday."
And you still got married. Great. So,
Yeah.
so,
And I still got married.
and the job was to work on the first chip, very first chip. So tell us about the issues that you faced with that chip and its development.
Sure. Now, I wanted to do two things before I answer your question. One is there's a special person here who worked on the first SPARC chip from Fujitsu. He flew in to US only for this event. I'd like to just have him come up and recognize him. It's Mr. Shigeru Fujii. Now, when we went to Fujitsu first,
Come on up, Fuji.
Yeah.
Fuji-san.
Thank you very much, Anand-san. So it was very exciting timing for me join to design of the SPARC fast chip. That's another big customer of me. Used to be at Fujitsu and Amudar are my big customer. But Sun selected my CMOS, 1.5 micron, 3-layer metal. But today, 28 nanometer. Wow, but still target power should be same. Let's make a good chip. Thank you very much.
Thank you.
the second thing, I'd like to thank all the people who work on SPARC and continue to work on SPARC. I've never seen such a strong dedication and desire to succeed, and I'd like to thank you all. And I'd like to recognize your hard work and effort that you put into it, so thank you. Challenges, oh boy. So,
Did we tell you there was only 15,000 gates on the chip?
So I came in, I worked with Robert Garner, Steve Mushnick, Bill Joy. By the way, if I say your name, it'll be great if you can stand up for just a second. So
actually, let's recognize the software, some of the software people where we are an integral part of this. Steve Mushnick, who run the compiler group.
Steve Kleiman.
Steve Kleiman.
Steve Kleiman. Where is Steve Kleiman? OS.
There he is. Right there.
All right. Steve had graduated from VEX, from AT&T, right? Yeah. All right. They came and joined Sun and did a tremendous job on the OS. A little bit later, we'll talk a little bit about the role of the software team in this project, because it's pretty phenomenal. It's not just hardware.
So some other people, Robert Garner.
Robert's here.
Ken Oken. Greg Papadopoulos. Steve Diamond. All right, so let's now answer your question. So yeah, I joined Sun. I was the first chip designer there. And I started working with Robert and others, as I mentioned, on the architecture. Of course, spent a lot of time with Patterson. And it was time to make a decision how we should implement it, and I made a decision to do it as a gate array because I knew that if it wasn't a gate array, it will get killed because the task would be too expensive, will take too long, and the company will run out of patience. Now the problem was we needed a gate array with about 20,000 gates. And there wasn't any available at that time in the marketplace. But through the grapevine I heard, maybe it's through either Synopsys or Mentor or Cadence, that Fujitsu was working in their labs on a 20,000 gate array. But unfortunately, it didn't have a memory. It was in 4 quadrants. So that's when we went to Fujisan and said, would you please design a register file for us? And he says, yeah, we can do that. How many ports you need? 2 read, 1 write. He says, forget it. It's too difficult. But eventually they pulled it off. So that was really the beginning of, that was not just a technical, but also a good business decision to make SPARC survive and prove the architecture that Professor Patterson and Bill worked on. Now, another interesting story about that is, so once we decided on this, Bernie, Bill, and I went to Japan the first time to meet with Fujitsu. And we decided to meet for breakfast before going to Kawasaki. Bernie and I are dressed in our black suit, white shirt, ties. And Bill walks in with his funky clothes. And Bernie and I are saying, God, we are a Japanese company, they're so conservative. What are we going to do? Well, fortunately for us, when we arrived to meet with Fujitsu, everybody there knew Bill because of the work he had done in Berkeley and Unix. And the meeting went extremely well. And we did eventually sign a contract with him. The final story in the first one, well, I can go on for. So I was designing the pipelines, and I had these little sheets of paper on which I had these pipeline diagrams, and I thought I was done every day. And then Bill comes to my office and optimizes everything, changes the pipeline diagrams. Oh shit, here we go again. So then I go work on it again. I was sharing an office with Robert Garner, and then Bill comes again next day, changes it again. Ideas were good, but finally Robert and I decided that we should close our door and not let Bill come in because we had to finish it to get it done. And at the same time, I was also, as I said, dating my current wife. She was in school, and we were having trouble because I was spending all my time at Sun, including weekends. So being a technical guy I am, or being a logical guy I am, I said, you know, why don't you come to our lab and do your homework there? While Masood and I are running simulations. And that's what happened. She spent her weekends in the Daisy lab doing her homework, and we'd take time off to go out to have lunch or dinner, and that was the start.
Thank you. So, Andy, the whole beginning of Sun started with your work back at Stanford, and but you were doing 68K based workstation. How did you first get involved with the SPARC effort and the stuff that Dave Patterson was doing?
Yeah, so I was not involved in the SPARC architecture, this first gate array at all. I was busy working on, cranking out one 60,000 workstation after the next. But then we had this problem that Motorola was late on the 60020 chip, I think it was called at the time, and it was just this unexpected delay, and there was nothing else to do. And this was around 1987, which is when the first gate array product actually got launched as a system product at Sun. So what was clearly missing from my perspective was a volume product that could deliver this very interesting CPU to the workstation market. And we ventured off to do this Unison company, because at the time, the Sun, the main company, wasn't quite convinced that SPARC really would take off, and I didn't want to fund yet another project. I had a friend at Next at the time, and I kind of heard what was going on there, and I was getting very concerned that it would pass us. But luckily, they were betting on the Motorola chip, which never arrived either. So here we are, and the first thing we decided was we want to do yet another SPARC chip. So we took the net list from the original chip and went to LSL Logic to get it cost reduced and to reduce the clock, increase the clock rate. And it was initially targeting 25 megahertz. We kind of missed a little bit. It came out at 20 megahertz, but then there was the second revision at 25. But the project was, in fact, announced in 1989, I believe. And this was actually the one time, at the time at least, where Sun lost money that quarter. Why? Because we didn't have any marketing people to sort of promote the SPARC station. So the forecast was, we're going to sell a lot of the 60,000 product and so on. But the demand immediately switched over to the new product, and we just didn't have enough product to ship. Publicly, the company claimed the conversion of the Oracle database at the time for the mishap, but it was actually poor planning. So that was 89. And then after that initial success, we got very busy doing the SPARC Station 2, and then we skipped 3 and went straight to 10 and 20. And basically, it was always a product around the next generation SPARC CPU. And I left Sun in 1995 for the first time, and that was a product designed for the Ultra SPARC machine, but that just came out when I left. So I was very busy doing, I think, 5th generation of workstations, which included SPARC chips.
So what challenges did the SPARC chips give you in building system-level products?
Believe it or not, none really. It worked just like a charm. And the key was, again, that we had a software team that could adopt the Solaris, and back then it was called Open, the BSD version of Sun Solaris, to the latest version of the memory management or whatever the new extensions were, and actually deliver this as a system product, hardware and software combined, just like Oracle is doing today. So without software, these things obviously wouldn't have worked. There was a concern early on that we wouldn't get third-party application software because obviously all the apps are running on the 68,000. But when people saw the performance numbers, they moved over in basically a couple of months. So that was actually a much smaller problem than people expected, even without a binary translator.
The binary compatibility was the big technical and commercial question about RISC, and it was, I think it's to the statement of the quality of the Sun compilers that people pretty much just recompiled and it ran. It was remarkable. People expected huge problems, but and I think the Sun compilers were very forgiving, right? They weren't strict on C. If it looked like C, it would pretty much compile it. And and I think, in contrast, the MIPS guys were to the letter, right? If it wasn't valid C, it wouldn't work. And I think they had a lot harder problems getting software to run on it.
And the other thing is we obviously had the NFS network file system, so people could build environments where they could share files between their installed base of machines and new SPARC machines. So it was actually a much more transparent upgrade to customers, if I may say so, than even the company itself expected at the time. So it actually went pretty well.
So Bernie is VP of Engineering. Sun is making a very big gamble here and starting its own microprocessor architecture and continuing that. Can you tell us a little bit about the business discussions that went around that decision and the decision to continue with it and possibly spin it out, or how to make that make economic sense?
Well, the fundamental reason is that we wanted to have systems that could differentiate themselves from the rest of the crowd. So what do you do to be different from the other guy? We had pretty much exhausted all the tricks in the book. I mean, I'm going to give you one of the tricks that we used. And at the time, Apollo was a big competitor of Sun. And we were sorting the Motorola chips so that Andy could design a machine without any wait state in the memory. Well, you can do that for only so many machines. I mean, if you try to ship 1 million machines, how many chips can you store, fast chips can you store to get the performance above the competition? So obviously something had to be done. And so the idea of building our own microprocessor was an obvious solution, as Vinod pointed out. Clearly, enormous risk associated with that. We had engineering problems. The company was low on cash, never done it before, no tools, no people except Bill and Andy and Dave Patterson. There was no
That's
expertise, basically. Actually, you are right on. That's enough. First of all, many people didn't know that it couldn't be done. So if you don't know it cannot be done, sometimes you can go and get it done. Then there was this debate at the board level to try to convince the board that it was the right thing to do. And Anand said he thought we were loonies. Well, the first time that I was in the board that the idea was presented, I remember Dave Marquardt was one of the investors. He almost threw me out. I mean, he said, what the heck are you doing? I mean, you guys are crazy. I mean, it makes no business sense. You just cannot do this thing. So the team, and I was just not one person, the team, and Vinod was a great proponent of the project, finally said, let's go and do it. And we knew the risks were enormous. That's bet your company, but if you don't take some of those bets, you are never going to be great. So that's really what drove us to go and do it. Yeah, it could have broken the company, but the will to go and get it done was there.
So, Rick, you joined the company a little bit later. When was that? What were you doing at the time, and why join Sun?
Sure. I was with Digital Equipment Corporation like Bernie, and I was there for about 15, 16 years. In the latter part of my career, I was working on EV5 and EV6 as system architect, and I became competitively aware of SPARC, of course, around that time, around the mid-90s. There was this benchmark that appeared called Stream, and if alpha was anything, it was performance leadership, and it was shocking to me that this company out west was leading us in terms of Stream. So like most companies, when you're behind on a benchmark, you find a way of gaming the benchmark, and so we actually produced a number for Stream that was clustered, and it's like, let's add up all the memory bandwidth of every PC in the world and publish that number. So that's how I became aware of that. And in '96, EV6 was nearing its completion, and it was feature complete at that point. And digital was going in that direction. We were under new management. Ken Olsen was gone. And so through a common friend, Ron Melanson introduced me to Anant, and I'm very grateful for Anant. He hired me and pulled me out here to the West Coast, moved my family, and that began my career at Sun. We were working on initially Millennium design and getting very aggressive at performance. And a couple of things we really try to do there is integration of more of the system components on Millennium, memory controller, et cetera, and looking at threading. So this is the early part of threading. There were Tulsa-Negger papers that were out there talking about essentially super scalar machines for wide issue that weren't achieving anywhere close to even one instruction per clock. And so with all these spare execution units, let's invent some threading. And so the threading model that we developed there was much like what appeared a lot in the industry at that time, and fairly clumsy, fairly complex, and not a lot of performance. What we really didn't get a good threading model until we did the Niagara, the FAR acquisition in 2002, and that really began the whole period of multi-threading, multi-core from that point forward. So the predecessors that you see from T4 that Mark was talking about earlier had its roots way back in 2002.
So I'll throw this out to the panel. So it was about '88 that Sun decided to put all of its wood behind one arrow and go with SPARC and the Sun OS. And of course, that was a whole ecosystem. It wasn't like a company like Motorola or Intel making the chip and depending on the rest of the world. You had to do the operating system, you had to do the system products, you had to do the compilers, you had to do the tools, you had to get the applications, et cetera. Can you say anything about that decision at that point in time?
Well, it was actually '89. So what happened was, at '88 there was still a major debate: is SPARC going to take off? And what we had Motorola. We also did an Intel product on the side, and there was the SPARC products. We actually had 3 internally competing efforts, to reach customers with things. But it was clear that SPARC had the most performance, but almost like I think at the time it was a factor of 3. So people looked at this from a cost performance standpoint, immediately concluded that SPARC was the way to go. So when with the success of the SPARC Session 1, and within I would say a year, it completely dominated all our shipments. It was clear that we might just bet on SPARC and forget about Motorola and Intel at the time.
So in the early days, after the initial gate array SPARC product, SPARC development was maybe not as organized or centralized or coordinated throughout Sun, but there was a point in time when there was effort to sort of focus. You at some point got into ECL and you got into gallium arsenide and you had, you know, I respectfully say kind of all over the place.
There was many flowers blooming.
By CMOS.
Oh, I think the thing was that as long as we could speed applications up by speeding up the clock rate, that was the right thing to do. And so these were ways of running the existing code base with more performance. But it also became clear at some point that we were going to hit the wall on clock rate just from, you know, the wire delays and transistors not scaling in the same way, so that we would need to go multi-thread. So there was always this belief that the best thing to do is just to go faster. And the whole industry is doing that now and about to crash into the 20 nanometer wall, where, you know, you're just not going to get new nodes anymore.
But
so what happens then is something has to change. In this case, it was going multi-threaded, right?
But at the time, what the RISC argument was is that we could do a 20,000 gate thing in a new fast technology, and it wasn't. You know, in retrospect, the power limited everybody, and CMOS was the way to go. But at the time, you know, ECL, gallium arsenide. I mean, pretty good designers. Seymour Cray was betting on gallium arsenide stuff. So there was this theory that, you know, a simple design could take advantage of new technology, and we'd have these tremendous clock rates. You know, the power, you know, limited all that, and CMOS was high power CMOS was able to deliver. And there were people at Sun who saw that, claim, you know, this isn't going to work. But I think Sun kept pursuing these other things. The other thing that Sun did right from the beginning was to say SPARC was a standard. And I don't know who made that decision, but it was an open standard. It's an IEEE standard. It's the only instruction set, I think, that's ever been standardized. And it played a pretty important role down the road. So I don't know who did that.
Who did that? Well, if you could comment this, there was a concern that if it was branded as this proprietary architecture, we would be no better than the IBM Power or whatever other architecture. And Sun was known as an open system company in terms of any kind of standard software hardware. So the conclusion was, let's just publish the instruction set, give it to the IEEE, and it's the only standardized IEEE instruction set out there.
Mm-hmm. So, Dave, yes, we did venture into ECL and gallium arsenide, and little known. So we were actually doing a server and workstation based on the ECL processor, but Sun decided to discontinue that because we didn't think the manufacturer, semi-manufacturer, could support the demand for Sun. And but little known fact that Cray continued to use that, and we did productize the silicon, and which eventually turned out to be a very, very profitable business when Sun acquired that business from Cray, because it was, I mean, from SGI, because SGI had bought Cray, and SGI didn't want anything to do with SPARC, so we got it, and there came out the E10K eventually.
Yeah, so because there was a standard, Cray, looking for new business models, started an enterprise thing, and what instruction set were you going to do? Where, well, Sun claimed you could use their instruction set and sell it. And the problem, you know, in talking to Forrest Baskett at SGI, who made this decision, why didn't they just kill it, right? When they bought Cray, they could have just killed it. And life would have been different had they done that. But there were customers who wanted to get this product, the standard, and so they sold it to Sun. And I think I remember the stories being both sides were happy with the deal, right? Both sides were thrilled that Sun would pay this much for it, and Sun was thrilled how little they had to pay for it. And then I basically, it was a 64 process thing that killed SGI in the marketplace, because 64 processors was a lot of processors, and they had the scalable architecture to go up to 1,000. But for almost all customers, a shared memory 64 processor, SPARC, was much more attractive than their main product line. So they kind of gave their enemy the tools to kill them, and I assume there's some business study about this.
But gallium arsenide, what happened there?
So that's an interesting story.
Right? It wasn't done at Sun.
No, we were doing the design, Andy, in conjunction with Vitesse.
Vitesse was it
at that time. Right. And at that time, while Sun was continuing to grow the business, Sun, Bill, Andy, Scott, and others realized that Super SPARC, which is internally called Viking, wasn't meeting the performance goals. And Scott actually called me in one day saying, I need you to start another CMOS processor group for the next generation of SPARC. And by the way, if you don't pull it off, you're not going to survive. So get it done. I said, I don't have a team. He says, go cancel the gallium arsenide program and put those people on the next generation CMOS, which then turned out to be one of the most successful products Sun has done, UltraSpark 1. And before we did that, we also, there's a person here, he should be here, Renu Raman. He started something called the I series of SPARC, which was highly integrated, very low cost. Andy loved it. And we made a very good business out of it. And
is Reno here?
Yeah.
Reno, stand up. There you go.
And we got a lot of help from Mentor at that time. I think it was GDT? GDT, yes. That was the first time we used these tools within Sun, and the product came out well ahead of its cycle time goals, ahead of Super SPARC 1, and that's when I guess Bill, Andy, and Scott got together and told me to go start that. So we had to kill now. UltraSpark 1 was probably one of the best teams Sun has had assembled. There are some people here like you to stand up, but let's not clap every time somebody shows up. Let's do it once they're all up. Ham Hinger, is he here? He was responsible for all the physical design. Nigel Ross is in UK. He was in charge of CAD, and he's the one who was a pain in the neck for Mentor, Cadence, and Synopsys. Sorry, R. He's the guy who was behind one of the best data centers Sun had put together. Today it has about 15,000 CPUs in it, and his vision was to make sure those CPUs are utilized 90% of the time. So I used to get a monthly report, and if the utilization of those machines was less than 97%, there was something wrong with it. Highly automated. Ron Melanson, I don't know if he's here. He was the guy who drove TI crazy because he wanted more and more performance. He had a team of process designers who actually help work with TI to define the process. Mike Splain, at that time, he was the guy who really was responsible for all of the verification, and no design could be taped out without his stamp of approval, and he is running the SPARC program now. Right, John? That's right. Okay. And last but not the least, Les Cohen, the Uber architect. I don't know if Les is here, but he's the guy who kind of came and helped us put the whole thing together. Les, if you're here, please stand up. He's here. Okay.
Stand up, Les.
Anyway, so answering to your question directly, yes, there was a lot of innovation going on within Sun. There were multiple groups. One under Dave Ditzel, who's here. Another one was under Jim Slager. I had a group. Ken Okin was also playing with pipelines at that time. And while there was a lot of innovation happening, we knew that we couldn't afford to do all of those things and dilute our efforts. And that's when the management team, I'm sure Bill and Andy were part of that decision, decided to consolidate all of that. And the first thing I did when I got that group was really create a roadmap for 5 years. We internally call it waterfall roadmap. And until 2000, we kind of followed that. There were no cancellations. We continued to execute very effectively. So consolidating that and coming up with a common product strategy, a unified product strategy that matched with the machines that Sun were doing. There was chips for servers, workstations, and low-end platforms for Andy.
So, Andy, I understand that at one point in time you'd looked at or thought about doing a low-cost workstation that had a different architecture than SPARC.
No, that's not the case. That was the spin-out thing we talked about earlier.
Okay.
It was based on the SPARC chip.
So, Andy, if I recall, you were my neighbor in Building 17,
correct,
in the corner office. And I thought you were thinking about doing something different. And you and I worked together to figure out how to do a unified chip.
Yeah, there was some early discussions on the network computer, which was kind of a early version of a cloud thing that even Oracle at the time was fancying. But it was a very low-cost, basically display device that would then tie into a server, and which actually over time did materialize. But it was basically too early when I was looking at this in the early 90s.
But I recall working with you and convincing you that LSI can actually do a very low-cost chip.
Yeah, we had this problem that I guess we didn't control pricing that well with our supply chain. So when Cypress did a chip, they wanted a lot of money for it, and it was actually too expensive to use in those workstations. So we had to go back to LSI to get a gateway built so we could get it for $50. So those are kind of problems we're dealing with.
Yeah.
So maybe Dave Patterson or Bill Joy can comment on this, but software was a key part of the success that made Sun successful. What were the key developments there that really worked on top of the SPARC processor?
Well, I think one thing that distinguished SPARC from the MIPS guys was a belief that the meaning of the program had to be enforced by the hardware, whereas MIPS had the theory that you could recompile for each machine because the hardware wouldn't interlock instructions, and that just never made any sense to me. I wanted programs to work on all the processors that we built, and was very focused on trying to get ahead of whatever instructions we would need so that we wouldn't be adding things, so that we would have backwards as well as forward compatibility as much as possible. And I think that's been a hallmark of the machines. And that made writing the compilers easier also. I think register windows made even the C compiler easier in the early days, although ultimately you would have to do, inlining and other things to get the performance. We got a head start on that by not having all that memory traffic for procedure call in the early days.
Yeah, I mean, you look, even though I do hardware, people don't really buy things just for hardware, right? So, wow, look at that cool hardware. It's got to run software to be useful, right? So, Sun had, a great operating system, an exciting operating system. And like I said, although it was a growing company, they had a compiler team that stuff really had to work, right? It wasn't just the performance. They wanted their customer software to work. People always ask me about register windows. I remember Steve Muchnick, okay, we're going to do a RISC machine. This is pretty early on, and Steve was responsible for having to do the compiler. He'd been on leave at Berkeley for a while, and then he came and joined Sun. And I said, well, look, if you're going to do a RISC machine, you have to do good register allocation. And at that time, the guys at IBM and John Hennessy had worked on graph coloring as a really great way to do register windowing. And given the size of memories and stuff at the time, Steve said, there's no way we're going to do graph coloring. We will not do graph coloring eligible. Well, then if you're not going to do that, you got to use register windows. Now, I think later, but it took a while to build SPARC. By the time it's shipped, maybe they had implemented the graph coloring. But
I'd also had the experience on working on the 360 series with IBM's Fortran compilers. And we had a Fortran G compiler, which was the equivalent of the C compiler. We had Fortran H, which is the equivalent of a register coloring compiler. And what you did is you had your program, and if you had 100 subroutines, you could compile 70 of them with the H compiler. Then there's the 30 that the register coloring didn't work, and so you could never optimize those. So my experience was that these optimizing compilers fail on complex programs in ways that
That's true.
You only have to empirically figure out what went wrong. It was beyond the state of the art, I think, to really do one of those against the set of code that actually existed. So we would have simply had the experience that customers would have compiled, and it wouldn't have worked.
Yeah,
and you say that the MIPS compiler rejected programs. Well, part of that is that they couldn't get the register coloring to work, probably, if they hadn't been more strict, because there would be hidden aliasing paths and other things. So I think it was really intelligent to not put the pressure both on the compilers but also on the application compatibility by trying to be so aggressive with what we would have done with rewriting the program in the compiler.
And the thing that Bill said earlier, I mean, the world was C and C++, but, you know, I had been at Berkeley, we'd had projects after RISC-1 and RISC-2. We had Smalltalk on a RISC and a Lisp RISC stuff. So we actually were doing more dynamic languages, and we actually did put instructions in. I think they've taken them out since. But there was support to do dynamic languages. And you know, and then Bill and others a few years later did do Java, which, you know, I remember this was his C++ minus language, right? A useful, he used to say that all the time.
C++ minus equals.
Okay. But he, you know,
a little bit more and a whole lot less. It was
a little bit more and a whole lot less. Yeah, it was very useful. You know, the C++ is very popular, but it's not going to go down in programming language history as a beautiful programming language. But Java was this, you know, much more attractive.
Well, Java was designed so that you could write an optimizing compiler because it didn't have the memory aliasing, which was the bane. Ultimately, the good thing about single cycle memory access and RISC was that it helped you with the fact that you couldn't get rid of the memory references because you couldn't tell what was going on in a C program because star A could be anything. So you couldn't hoist things into registers to get speed. You had to have fast cache access to run the programs quickly.
I really like to maybe comment a little bit about the importance of software in the SPARC program. Because I mean, we talk a lot about hardware, which is the embodiment of an architecture and what the customer sees. But the software was so fundamentally important. And I say Sun recognized very, very early the value of the integration of the hardware and the software together. And building that software team, whether it be the compiler team with Steve Mushnick, the operating system teams, or the networking guys, to really tightly integrate that piece of software with the hardware was so fundamental to getting the performance into the system. And also in preserving the environment, the investment that the customers had made in their applications. Those compilers could take a piece of software, like was written for another machine, and make it work. And that is really something, that integration is really fundamental. I think nobody more than Sun, and perhaps today Apple, understands the value of that tight integration of the hardware and the software.
Well,
yes?
Clearly, the semiconductor companies couldn't do that. Intel and Motorola, Zilog couldn't do that. But HP and IBM, as well as Sun or MIPS, could have done that. But somehow you managed to do it better than anyone else. Why was that?
Because there was no choice. It was either doing it or failing.
But so it was a really good, the quality of the engineering was amazing. I assumed it was because of, you know, Bill Joy and Andy Bechtolsheim were very well known and admired, and I assumed they acted as magnets to build this really first-rate team. And so it had the kind of that startup company mentality with the whatever 200 engineers that covered that whole breadth, really 200 really good engineers that covered that whole breadth is, I assume, why it pulled it off.
But we always were a system company, right? There was always a system spirit of an IBM or DEC at the time.
I guess the answer then is IBM and HP were systems companies, but they had other things to depend upon. Yeah. Your life depended on each development.
But there was one hardware feature I wanted to highlight on the SPARC architecture roadmap, which is SPARC was in fact one of the early CPUs that adopted the 64-bit support with AutoSpark. And of course that required equivalent software support, but you know, this was, 10 years ahead of Intel supporting 64-bit on the mainstream architecture. So it was a significant advantage being able to support large memory and virtualization.
Yeah, and that was a product line that really propelled Sun into, what, $16 billion. And that was one of the most successful product.
Yeah, we're-
Now, Dave, hang on. Dave, I see Steve Mushnick there standing up.
Yes.
Yes.
Here, let me give you
So
a
while he
microphone.
walks up, let me give you a little anecdote of the first SPARC machine. So when the chip started wiggling, you know, everybody was really happy because it was wiggling. Then we started measuring the performance, and it was about 2 times the performance of the Motorola machine. Not good enough. I was so mad at this thing that I got the people together, Mushnick, Kleiman, and company, and the software guys pulled it off. They optimized those systems, so that we ended up with about 4.5 times the performance of the Motorola machine. Because of that integration, the role that the software guys played, taking that piece of hardware and make it in hum with the right coding. All right, Steve.
Thank you. For those of you who don't know me, I am Steve Muchnick, and I led the compiler team for SPARC and for the 68,000 machines before that. I have 2 stories to tell. One of them is that we worked very, very hard to port the compilers, and I had a great team working under me. I don't know whether any of them are here. But the second thing is that I appeared before the board of directors, or not the board of directors, the executive team under Bernie, every month when we were developing SPARC to report on performance. And I had Bernie telling me, you've got to get more performance, more performance, more performance, more performance. And finally, we managed to do it. And that's all I want to say.
Thank you, Steve. Well, we're going to get John Fowler up here in a few minutes to tell us a little bit more about the future of SPARC. But Rick, you're a key part of that. And can you tell us where you see things going and where the innovation's going forward?
Well, going forward, I think it's more cores, more threads, and even higher clock rate on SPARC. There was we're at T4 right now. It's shipping now since about a year. T4, we started out the whole Niagara program in 2002, and that threading model that we developed in 2002 is contained on the T4 core, and it's got a combination now of high-speed single-threaded along with throughput through the threading model. So in future, I see it. Again, we'll continue to turn up the clock. I don't see that stopping in the near term. It may at some point. Power definitely is our limiter at this point. How much power we can actually get on the chip. We are building much larger die than we did in the past. I had a rule from Mike Splain and David Yen. 300 square millimeters was it on the original Niagara programs. We held in there with it right now. In fact, T4 is competing with 560, 600 square millimeter dies, and it's only about 400. So in future, you're going to see larger and larger die, probably as large as we can possibly print. The phenomenon of what's happening in development in the fabs is really quite strange. Because it was the curve looking like this. If you got above 300 square millimeters, your yields would go dramatically lower. That's not really the case today. So I do see a lot more frequency. And again, from the Oracle perspective, there was comments earlier about how much integration software had with the silicon. We do that from conception. From the moment we conceive of a new design, we are analyzing Oracle database on that new design as we craft that technology. From the moment we begin, we can apply both operating system and applications in the development of the processor. That happens from day one. And now we have the ability to predict within 4 or 5% future performance. From a 5-year program, from the moment we conceive, we can anticipate the performance and hit it within about 5%. So that's how mature that technology has gotten in terms of performance modeling and verification.
That's great, thank you. It's interesting that you said since 2002, threading has been the key issue, and Bill mentioned at the very beginning, he insisted to put support for threading in the architecture. So it just shows the vision and the capability the team, the original team, and ability to keep that going.
Yeah, I thought there was a lot more vision to the naming of SPARC than what Anand offered. So we have products now that are 1,000 cores and, well, 1,000 threads in a current systems that we're developing today. Under one instance of the operating system is phenomenal.
Okay, before I dismiss the panel here, let me just very briefly introduce John Fowler. He's going to come up here. You don't have to dismiss him, just leave him up there. Oh, okay, I'll leave him up here. So he's Executive Vice President of Systems at Oracle. And before Oracle's acquisition in 2010, he worked for Sun for more than 14 years. And he served in several influential roles, including Executive Vice President of Sun's x64 Systems Group, and at Oracle he continues to be responsible for delivering all the Sun stuff.
That's good. So you're overstating me, because at Sun, all you are is a manager of these kinds of engineers. You're a host manager. Okay, you're not actually getting to do stuff. So I'm responsible for hardware at Oracle and was responsible for hardware at Sun during latter stages. And I'll start the modern era of SPARC with my first meeting with Larry Ellison. So Oracle announced they're buying Sun. I don't know Larry. I have no idea what that's going to be like, right? So pretty excited because I understand what the software means, and you spend all your time working on hardware trying to get somebody to pay attention to you, and we're suddenly in a company that has a huge amount of software. So, but I didn't know anything else. Now I know Larry likes hardware because he has planes, boats, and cars, right? So going in, I figured, okay, this is going to be good. He likes hardware. He's got a lot of it. So, like most executive managers, you memorize a lot of facts before a meeting so that you actually look smart in the meeting. So I memorized many, many facts about lots of things, and I go to meet Larry Ellison. And Larry walks in. For those of you who don't know Larry, he really doesn't do the pleasantry stuff. There's no, hi, how you doing? How are your kids? You're looking well today. So he walks in the room. He looks at me and says, "What are the cache sizes of all your processors?" And I sat there going, oh crap. I mean, that's like the one thing I didn't memorize. Okay, so I had head count and OpEx and margin and regions and all kinds of stuff that he didn't really care about. But it's a very important point, which is Larry was phenomenally interested from the very first day on what could he do with silicon, what was possible, what could change, and what could he do. And the mission he gave the team was pretty straightforward, which is what are we going to go invest in this technology to get it back on top. But there's a twist at Oracle, which is we are willing to go and do things to think about the system as the whole system, which includes the database, the middleware technology, the storage, and all of those things. And so now today, under Larry, he did a bunch of other things that are kind of interesting. One of the things that he did was he eliminated speed bumps. So when Mike Splain and I used to wander in, which you do in processors every once in a while, is you throw in a speed bump, right? Because you got to do something with the people. And Larry would go, no. Right, you're going to double every time. So we now call that Larry's Law, because we say, hey, it's kind of hard to double every time. He says he doesn't want any speed bumps. He doesn't want doubling every time. But right now, today, we have, I have 3 processors, 2 of which are in production ramp, and a third that's in silicon that'll be coming out next year. And we're design complete on the 4th one, and it's a tremendous acceleration of the innovation around the technology. The twist is we now have co-development teams with the database and with Java and others. And just to give you a feel for thinking about the system is in our next generation processors. For example, we're building in co-designed with the database clustering team the ability to use our coherent memory interfaces as incoherent, very high-speed buses for clustering with all the proper semantics built in, because we're thinking about the whole system level interface. We're building in technology to actually operate against compressed databases at full OLTP transaction rates. So combined with threads and cores and caches and just being aggressive in the design and process technology, we also have the freedom now, whether it's in the database or the operating system or the silicon, Larry considers that all his field of use. What can we go put in? And as Ricky would tell you, we have instruction traces and real data and stuff, and we look at the microarchitecture of every aspect of enterprise software. And through that now, over the next year, 2 years, you're going to see some impressive, incredible capability jumps in the SPARC architecture. both for running all of the existing applications, but also for what we can do as we're welding together storage and networking, because we comprehend those when running these database applications. Now, the one thing we are concerned about is we have properly frightened our sales teams, so they're not here, because these capability jumps are so incredible that we are, in fact, as Mike explained and I joke about, we're seeking new interpretive languages that will consume enormous amounts of computational bandwidth, because we're going to need it very soon to keep the business model afloat. So anyway, I want to, obviously I wasn't a part of the early history. I'm the later host manager, but it's been very exciting to be a part of that. Larry has got silicon on the brain. Mark Hurd talked about that. He's got an unhealthy obsession with hardware, and so we have to go slake that obsession. But it's really exciting to have the co-engineering between the software and hardware teams, as well as the investment profile and attitude that Larry has to go after this and really go take some risks in, what do we put in the processor, and then how do we co-engineer some of these things for step functions and performance and capability. So I'm glad all of you joined today, and now I'll turn it back over to you guys.
Okay.
Just 3 quick things in closing, ladies and gentlemen. First of all, please join me in thanking Dave House and this wonderful panel. And also Vinod Khosla for being here, Mark Hurd and John Fowler of Oracle. Thank you so much.